Hi, this is Kate, and this is the Day 1 video for Math S-323, Vectors, a tool for teaching algebra, geometry, and trigonometry. Now this is not an online course, but unfortunately the start of the Math for Teaching Week 1 summer session has overlapped with the end of the school year for many of the teachers in this class, and so I decided to offer some of the opening lectures online as a way for these teachers to be able to still take this class but not fall behind. Let's get started. As we delve into the world of vectors, we have to start with one of the most basic building blocks of mathematics, which is fields. What is a field? First of all, a field is just a set of elements for which the familiar operations of arithmetic and multiplication are defined and behave in the usual way. And really, the reason it's quote-unquote the usual way is because more often than not, when we're teaching math, when we're talking about math in the K-12 area, as well as a lot of college mathematics, we're always working in fields. Here are the set of axioms for a field. Axioms are a set of rules. For fields, we have quite a few. Let's take a look. One is that addition is commutative, so changing the order of two elements of a field and adding them together doesn't change the sum that we're looking at. So a plus b equals b plus a for any two elements a and b of the field. Addition is associative. If we group the sum of a and b and then we add on c, that would be the same thing as what we would get if we took a and then added on the sum of b and c for any three elements a, b, and c of the field. The additive identity. Now, before I even say this out loud, there is some mathematical notation involved. We have this backwards E here, which means there exists. We also have an upside down A, which means for all. We have this weird sideways sort of pitchfork, I always say, but that means element of. So when we string that all together, what this mathematical notation allows us to say with way fewer words is there exists a zero element such that for all A that are elements of the field, so that means there exists a zero such that for any element of the field F, 0 plus A is equal to A plus 0. That's true by commutativity up here, but that 0 added on to any element of the field just gives you that element back. A plus 0 equals A. You might say that's not earth-shattering at all. That's because we are always working in fields almost all the time when we're teaching algebra or geometry or trigonometry. We're always working in fields. Additive inverse. Let's see here. Translating our new fancy mathematical notation, this means for all A, and we have element of the field, so that means for all elements of the field, for any element of the field, there exists minus A, such that minus A plus A equals A plus minus A. That's commutativity again. But when you add the additive inverse of an element to itself, so A plus minus A, we're going to get 0. Does that make sense? You can think about this in terms of the real numbers. 3 plus negative 3 equals 0. There's multiplication too. Multiplication is associative, so the product of A and B multiplied by C is going to be the same thing as A multiplied by the product of B and C for any three elements A, B, and C of that field. Multiplication is commutative. A times B is equal to B times A for any two elements A and B of the field. We have some more mathematical notation here. So we have a multiplicative identity. There exists some element known as that is the multiplicative identity, such that for all elements of the field, so for all A that are elements of the field, 1 times A equals A. There's also a multiplicative inverse. Now this is a little trickier here because we're used to, okay, for all A in the field, so for all elements of the field, but it's not just the field, it's F minus this, 0. So this means the set that is left over when you take the field and you subtract off the 0 element. So what this really means is for all elements that are in the field without the 0 element, so all elements of the field but not the 0 element, there exists an a to the negative 1, or a inverse. I hate saying a to the negative 1. A inverse. Such that a inverse times a is equal to 1. And that's of course true because we would not be able to say for all elements in the field there exists a multiplicative inverse because 0 doesn't have a multiplicative inverse. So that's why we say for all elements in the field other than the 0 element. So the set of elements that are in the field but not including the 0 element. And last but not least, we have the distributive law. A times B plus C equals A times B plus A times C for any 3 elements in the field, A, B, and C. And that's it. Those are the 9 axioms of a field. One thing that people always point out to me is they say, hey, there's no subtraction, there's no division. What is that? Well, in fact, this additive inverse defines subtraction, and this multiplicative inverse defines division. We don't need to define subtraction and division as separate operations. And in fact, a good deal of you algebra teachers out there are always trying to convince your students to, instead of thinking as division of a separate operation, think of it as multiplying by the inverse. Instead of thinking of subtraction as a separate operation, think of it as adding, the additive inverse. And also, this is not an independent set of axioms. When I say independent set, that would mean that none of the axioms could be proved using the other axioms. In fact, number 1, that addition is commutative, can be proven using the other axioms. It's common, especially when some of these are so popular and so necessary when we talk about axioms, to include them on the list even if it's not independent, even if one of the axioms can be proved by some of the other axioms. So this is not an independent set where each axiom is independent from the other and can't be proven from the other. Some of these can be proven from the other axioms. Let's take a look at the next page here and start practicing some basic rules that we sort of take for granted working in fields, but how do we prove these statements with just the 9 axioms on page 1? So our first question is, using the field axioms, prove that if A times B equals 0, so if the product of 2 elements in the field is equal to 0, then either A or B must be 0. One or other of these elements must be 0. Also, remember that in mathematical or deductive logic, when we say the statement either A or B must be 0, that means that A could be equal to 0, B could be equal to 0, but also A and B could be 0. If A and B are both 0, the statement A or B equals 0 is true. So, what we're going to do, the general structure of this proof, is that we are going to assume that the product of A and B is 0, and then we're going to look at the 2 cases, because A is either 0 or not. And so the structure of this proof is going to say, okay, we're going to assume that the product of A and B is 0, and then we say, if A is 0, is the statement A or B must be 0 true? And then we're going to look at the second case, which is A is not 0, and then we're going to see whether the statement A or B must be 0 is true then as well. Let's get started. All right, first thing, we assume the if part of our statement. We assume A times B equals 0. Now, let's look at the 2 possible cases for A. Because if we consider the case where A is 0, and we consider the case where A is not 0, those are all the possible cases. There's not another option for A if A is an element of a field. It's either 0 or non-zero. There's no other type of element. All right, case 1. A is equal to 0. Now, we see if the then part of our statement is true. If A is equal to 0, is the statement either A or B must be 0 true? It certainly is. A equals 0. The statement A or B must be 0 is true. I know it's trivial, but to do a formal proof, you really need to go through both cases. Now, of course, for the trickier one, the second case. This is the case where A does not equal 0. Can we say that either A or B must be 0 is true in this case? Well, we're not really sure. We don't know anything about B. We know that A is non-zero, but we don't know anything about B yet. Let's take a closer look. We know that A times B equals 0. Now, here's what I'm going to do. I'm going to multiply both sides by the multiplicative inverse of A, which I know exists because of axiom number 8. Any element that is non-zero in a field has a multiplicative inverse. Note that I am very clearly justifying the existence of this multiplicative inverse by the axiom on that line, and that's a key point to this type of proving, that you need to cite exactly what axiom tells you that this multiplicative inverse exists. Well, let's see here. A inverse times A simplifies to 1. This I know is true also by axiom 8, both the existence of the multiplicative inverse and the fact that A inverse times A equals 1. Those are both statements of the 8th axiom. Now this left-hand side, 1 times B. Well, taking a look at our list of axioms, 1 times B is equal to B, and that is true by axiom 7. The existence of the multiplicative identity that tells me that for any element in a field, 1 times the element is just the element itself. So I can simplify the left-hand side to just B by itself by axiom 7. Now let's take a look at that right-hand side. A inverse times 0. A inverse times 0 is equal to what? Well, you would be absolutely right in saying that anything times 0 is equal to 0. So we can simplify that right-hand side down to 0, and lo and behold, we've deduced that when A is non-zero and the product of A and B must be 0, we've used these axioms to deduce that B is equal to 0. Now you might be saying, hold up for a moment, Kate. What was your justification for being able to simplify the right-hand side that was A inverse times 0 down to 0? It's not one of the axioms, and you're absolutely right. And in fact, the proof that for any element of a field, A times 0 equals 0 is going to be one of the proofs that you will do in your small group problems, in your group work today. So this justification here is intentionally left missing so that you can see that you're actually able to prove the fact that any element times 0 is equal to 0 is something that you can prove with these other axioms. That's a sneak peek to later. But here, we've successfully proven what we set out to prove. Yes, there's a little bit of a justification missing here. If this showed up on a test, I would absolutely allow you to say, as proven in class, because you all are about to do it, A inverse times 0 is equal to 0. But that's the justification that's missing on this line, which I will just put a little question mark here, little mystery. But in total, this entire proof is complete. We assume A times B equals 0. Our two cases that we separate to sort of organize our thinking is, okay, well, if A is 0, then obviously the statement A or B must be 0 is true. If A is not 0, is the statement A or B must be 0 true? Well, we start out with this fact, and we use axiom 8, the existence of a multiplicative inverse, to simplify the left-hand side into 1 times B. That's a multiplicative identity, which gives us B on the right-hand side, and then we have A inverse times 0, which is going to be 0, which again, you guys are going to prove today. And so we have the case where if A is 0, that's true. A or B must be 0 is true. If A is not 0, B must be 0. And so the statement A or B must be 0 is true there as well. Let's take a look at the next proof. It says, using the field axioms, prove that minus A, remember that minus A is the additive inverse, is unique. Well, first of all, what does unique mean? Well, that means that for any element A, it only has one additive inverse. Its additive inverse is unique. So there's a very standard way to prove uniqueness. And the way to do that is to say, okay, let's assume that in our minds that the additive inverse is actually not unique. Well, what does that mean? What does the additive inverse do? When we take an element and we add its additive inverse onto it, it gives us 0, right? We can flip back our page to axiom 4 on page 1, and that tells us what the property of the additive inverse is. And so the way to prove uniqueness is you pretend like you've discovered something else that behaves just like an additive inverse. I'm going to call it B. All right, that means that I've discovered something where A plus B is equal to 0. B's name is not minus A. How weird. All right. Well, what am I going to do now? I'm going to show that B must be equal. B, this mystery thing that also behaves just like an additive inverse, must be equal to minus A. All right, let's see how this works. Well, I'm going to add minus A onto both sides of this equation. Let's see what that's done for us. Well, when we take a look at what's happening on the left-hand side, minus A plus B, if we flip back to the front page, minus A plus A is equal to 0 because of the existence of the additive inverse. This was the additive inverse. So these two terms here simplify to 0. Let's write that in. So by axiom 4, the existence of the additive inverse, we know that minus A plus A equals 0. Now we're left with 0 plus B on one side and minus A plus 0 on the other side, and we know that 0 happens to be the additive identity, right? If you add 0 to any element of a field, you're just going to get that same element back. So that means that we can simplify the left-hand side to B by itself, and we can simplify the right-hand side to minus A by itself. And look at that. Lo and behold, we said, oh look, maybe there's a mystery element that behaves just like minus A, but it's not minus A. This is sort of assuming that the additive inverse is not unique. But as it turns out, after manipulating this algebraically, always obeying the axioms of a field, it turns out that B and minus A are the same thing. This is how we prove uniqueness, that you assume that it's not really unique, that there's something else that behaves just like minus A. In fact, that's not true. This thing is equal to minus A. So the only way that you have something that behaves as an additive inverse must be that it's equal to minus A. It is minus A. So that's how you prove something is unique, and in particular with this proving minus A is unique. You'll be charged on your homework with proving that the multiplicative inverse is unique. So how would you go about doing that? You would probably start off by assuming in your head that the multiplicative inverse is not unique, that there's some mystery B that behaves just like the multiplicative inverse, so that A times this mystery B would be equal to what? I'm not going to answer that. You'll have to think about it a little bit on your own. Let's take a look at some more common fields that we've been using forever and ever. All right, basically all of the math that we do in K-12 education and much of college is dealing with fields. The rational numbers are a field. And in fact, look, that when you learn to add and multiply fractions, when you teach your students how to do that, when you teach your students how to not think about division as a separate thing from multiplication, but instead multiplying by a fraction, you're actually proving that the rational numbers are closed under the operations of addition and multiplication. What does that mean? That means that if you add two rational numbers together, you'll get another rational number. If you multiply two rational numbers together, you'll get another rational number. The reals are also an example of a field. When you learn to add and multiply decimals, you were close to proving that the real numbers are closed under the operations of addition and multiplication. In fact, those infinite decimals are really difficult to prove commutativity and associativity, but it can be done. And the complex numbers are also a field. I believe we touch on complex numbers in algebra, or at least I did. Maybe it was pre-algebra. I think it was algebra. And a little bit again in high school. So when you learn the trick of multiplying the numerator and denominator of a complex fraction by the complex conjugate of the denominator, you're actually exploiting the existence of the multiplicative inverse of the imaginary component. Something is not being included on this list. That is a really common set that we use a lot in mathematics. And in fact, it is the integers. The integers are not listed here. Note that they're not listed as an example of a field. And you may want to pause this video for a moment and think to yourself, look over that list of axioms. Which of those axioms does not hold for the integers? I'll give you a moment. If you said multiplicative inverse, you would be correct. Think about that for a moment. For a field, within that set of elements, every element needs to have a multiplicative inverse. Let's take a look at the integers. I'll pick one. How about 4? The multiplicative inverse of 4 is 1/4. But note that 1/4 is not an integer. It's not a member of that set. And so the integers themselves are not a field. However, there is a way to convert the integers into a field. They're called finite fields, and that's going to be the topic of our next section here. Let's take a look. Here's how you do it. The first step is that you have to choose a prime number p. Then what you're going to do is you're going to break up the entire set of integers into p subsets, and here's exactly how you do it. Each subset is named after the remainder you get when you divide that integer by the prime number p. So this subset right here, 0, you see this is some more weird set notation, but when you see a curly bracket, it means the set of, and so 0 means 0 sub p, really, I should say. That's the set where the elements are called m. It's just a random name that we give them. So the set of elements, this straight line here means such that m equals n times p, where n is an integer. So what does that really mean? This means the set of elements such that each element is equal to an integer times that prime number. So that basically means these are all the things that are exact multiples of that prime number. When we look at 1 sub p, that's the set of elements m such that m is equal to n times p plus 1. That means that these are all the integers such that when you divide by that prime number p, you're left with a remainder of 1. And in general, this can go like a sub p. That's the set of elements such that when you divide by those integers by the prime number p, you get a remainder of a. Let's take a look about how to define addition and multiplication with these particular finite fields. Addition is pretty straightforward. A sub p plus b sub p is basically equal to the sum of a plus b sub p. Don't worry, you'll see exactly how this works out when we're about to do some sample problems here. So the idea is we add a and b together, then we divide by the prime number p, and whatever the remainder is what we want to keep, what we name this after. Define multiplication. A sub p times b sub p equals a times b sub p. So again, a and b are the names for the subsets because really the answer is independent of the choice of the name. The rule here is we take a and b, we multiply them together, then we divide that product by the prime number p, and we keep the remainder. I left a nice proof here that the multiplicative inverse exists. It's sort of for your own personal enrichment, but we'll just be looking for multiplicative inverses as we do some of these sample problems. So let's get started with some nice sample problems. It might seem overwhelming at first. What is this remainder? What is this? A lot of people learn about finite fields using the term modulus. That may be something that is more familiar for you. But let's take a look at some sample problems to get your feet wet with finite fields. All right, it looks like we are in Z5 here. So our 5 elements are 0, 1, 2, 3, and 4. So our first question is find the sum 3 plus 4. Well, the way we do that is we just want to sum what's inside the brackets. Well, 3 plus 4 is equal to 7. But note that this is not reduced. The only elements of Z5 are 0, 1, 2, 3, and 4. 7 is not an element, but What is 7? 7, when divided by 5, has a remainder of 2. So the reduced form, when you want to write 7 in Z5, the way you really should write that is 2. And that is your final answer. Let's take a look at number 2, the product of 2 in Z5 and 3 in Z5. Well, following our rules before, all we have to do is just take the product of 2 times 3. That gives us 6 in Z5, but there is no 6 in Z5. In fact, 6 is one of the members of 1, right? Because when 6 is divided by 5, we have a remainder of 1. So far, so good. Yes? So there, within 0 sub 5, there are an infinite number of integers that are all equal in 0 sub 5. Those are all the multiples of 5. In 1 in Z5 are the infinite set of integers that have a remainder of 1 when divided by 5. 2 in Z5 are the infinite set of integers that have a remainder of 2 when divided by 5. And same for 3 and same for 4, and of course, there is no remainder of 5 when you divide by 5, because that would just be another factor. You would be able to divide by 1 higher. There's no remainder of 5 when we're dividing by 5. The additive inverse of 4 in Z5. Well, what does the additive inverse do? Remember that the additive inverse, you're supposed to be able to add to 4 and get 0. So what do we need to add to 4 to get 0? Would it be 0, 1, 2, 3, or 4? If you think 1, you would be correct, because take a look. If we take 4 in Z5 and we add 1 in Z5, we end up with 5. But there is no 5 element. In fact, 5 is just equal to 0. So we're looking for what element in Z5 can you add to 4 and get 0, and that's going to be this guy right here, 1. Continuing on, the multiplicative inverse of 3 in Z5. Well, what do we want a multiplicative inverse to do? We want to be able to multiply 3 by something and get 1 back. Now this is tricky. We want to get 1 back in Z5. So you kind of want to play around with trial and error. Should I pick 0, 1, 2, 3, or 4? Take a moment, pause the video, try it out for yourself. Okay, let's see here. It's actually going to be 2, and here's why. When we take 3 and multiply it by 2, that product is going to be 3 times 2, which is 6 in Z5, but of course there is no 6 in Z5. 6 has a remainder of 1. When divided by 5, 6 is equivalent to 1 in Z5. So 2 here is the multiplicative inverse that we are looking for. Let's see how we do with number 5. The quotient 2 in Z5 divided by 3 in Z5. We essentially want to be able to reduce this down. And remember that each of 0, 1, 2, 3, and 4 actually are an infinite set of integers that each have either 0, 1, 2, 3, or 4 as their remainder when they divide by 5. So what we really need is we need to pick a different numerator. A numerator that still has a remainder of 2 when divided by 5, but that evenly divides by 3. Take a moment, think about which one you'd pick, pause the video, and then come back. Okay. Which one should you pick? Well, let's just start looking at what are all the integers that 2 is equivalent to. 2 in Z5, I should say. Well, first there's 2, and then there's 7. 7's still not divisible by 3. Then there's 12. Aha! 12 is definitely divisible by 3. 12 divided by 3 is 4. Please note that on exams, this is not an appropriate final answer because 12 in Z5, there is no 12 in Z5. These are sort of messy, unsimplified versions of how you should sort of think through these problems. You might be wondering, well, what if I hadn't noticed that 12 was a member of the set 2 in Z5. What if I had just like breezed right past it? Well, let's take a look. What's the next one that's divisible by 3? There's 17, there's 22, there's 27. 27, you say, is divisible by 3. Well, 27 divided by 3 is 9. 9 is not a member of Z5. 9, when simplified, has a remainder of 4 when divided by 5, so it is actually also equal to 4. So it doesn't matter if you don't get the exact lowest possible simplification opportunity. It will still give you the right answer as long as you simplify at the end. Now you might be wondering, what do fields have anything to do with vectors? Well, in fact, they have everything to do with vectors and points. Because in fact, the components of vectors are members of a field. The components of points are members of a field. So let's take a look down here of field elements as points and vectors. When we use this notation, Fn, that denotes the set, usually an infinite set of ordered lists of n elements from the particular field that is listed in F. So usually you don't just see Fn, you see something like this, R2. Well, that means the set of ordered lists of 2 elements from the field of real numbers. Now, ordered elements means that order matters. If you look at the point 1, 2, that is different from the point 2, 1, right, in the coordinate plane. It matters which location the values are in. You don't always have to use the real numbers. For the most part, we will have occasional explorations into the field of complex numbers, but for the most part, we'll be dealing with R, as almost everyone does in their math classrooms everywhere. But it is, as far as points and vectors go, you could be using complex numbers, you could be using finite fields. Those are all fair game. The issue with points and vectors is that those components are members of a field. And so that's why the particular operations of addition, subtraction, multiplication, things like that, that's why they are defined in particular ways and behave in what we consider normal ways, because we always use fields. But that's why we can exploit those axioms, because the components of points and vectors are members of some underlying field. So let's take a look here. When we're looking at a point, we consider that position data. When we're thinking of a vector, that means incremental data. So a vector, the components of a vector represent change. The components of a point represent our current status, so to speak. Let's take a look. Many textbooks sort of ignore that distinction, that vectors are increments of change and points are sort of our current allocation of resources. Let's take a look at how we want to notate them. With points, we always have parentheses, smooth parentheses there. And then this particular point, we want to bold this. I understand that when you're doing your homework by hand, it's impossible to bold, so you don't need to. But, you know, when you're looking at a textbook, you'll always see points are bolded, usually with parentheses used. So when we look at this 1.1, -3.8, 2.3, what's the geometric significance of this? Well, it is the location specified by 1.1 units in the x direction, -3.8 units in the y direction, 2.3 units in the z direction. Its distance from the origin is the square root of the sum of the squares of the components. That's a generalization of the Pythagorean theorem. Once we move out of R2 into R3, that Pythagorean theorem still gives us the basis for how to compute distance from the origin. So it's the square root of the sum of the squares. In this case, it would be the square root of 1.1 squared plus -3.8 squared plus 2.3 squared. So that's how we talk about points. When we notate vectors, now we use a bold letter. We put an arrow over it. It's so important for you guys in your work to, if you're talking about a vector, put that arrow over it. And we use square brackets. So here's a vector, -0.2 1.3, 2.2. How is this different from our point? Well, it's not talking about a location in space or a location in the plane. What it's talking about is an increment of change. So it's saying this is a decrease of 0.2 in the x direction, it's an increase of 1.3 in the y direction, and an increase of 2.2 in the z direction. What are the uses of points and vectors? Let's take a look. The first is that we can add a vector component by component to one point to get to another point. So we want to start at point A and get to point B. How would we do that? Well, we add a vector onto it. That vector indicates the appropriate increments of change in the x component, the y component, and the z component, or if you're in the plane, just the x and y components, to get to the second point. And in fact, this is really important to note, is that geometrically, when we're drawing things in the plane, we're very used to drawing points, right? We have point A and point B. How do we visualize what the vector looks like that takes us from A to B? Well, it looks just like this. It has a length, magnitude, and direction. And the x component here of the vector tells us the increase or decrease in the x direction, and the y component here of the vector indicates the increase or decrease in the y direction to take us from A to B. Note that vectors are not defined by their anchor points. Because vectors are only increments of change, they could take you from any point to any other point. It just indicates how much x and y are changing from one point to another. As long as those 2 points have the same relationship to each other, you can move that blue vector around and say, hey, what if I had C down here, and then I took that blue vector and anchored it at C, and oh, I'd have another point D over here, and C and D would have the same sort of spatial relationship that A and B have, just in a different area of the plane. But we'll get more into that a little bit later. One thing that we can do is we can subtract point A component by component from point B to get that vector. So we could actually computationally, subtract A, whatever the values are for x and y, from B, and we would get exactly what the necessary increments of change would be to go from A to B. Vector addition, if adding V to point A gives point B, and adding W to point B gives point C, then adding V plus W to point A gives point C. Well, what does that look like? Let's set it up. Well, here's what this problem is telling us. If we have the vector V, which when we add to A, it gives us B, and we have the vector W, which when we add to B gives us C, then we're saying that adding V plus W to point A gives point C. And you could think of V plus W here, but also this indicates how to add vectors together. We line them up nose to tail, so it goes tail, nose, nose. And then the sum of V and W can be visualized right along here, going from the start of V to the end of W. And of course, V plus W, when you add that onto A, will take you to that endpoint. After you've traveled V, after you've traveled W, you're at C. And a vector in whatever field you're in, Fn, can be multiplied by any element of that field to get another vector. So what does that mean? Well, if we have something like the vector 1, 2, right? That's an increase of 1 in the x direction, an increase of 2 in the y direction, and we wanted to multiply that. Note that this is in R2 because these are two real numbers. And I want to multiply that by 0.5, say. What does that look like? Well, computationally speaking, if I wanted to take 1, 2 and multiply it by 0.5, that just means that each component is multiplied by 0.5. So now I have 0.5 in the x component and 1 in the y component. Visually, what does that look like? Well, it's absolutely parallel to the vector that we had before, but it's just half as long. That's what it would look like. Let's take a look at some sample problems. Before we begin them, it's important to sort of take a look at what makes sense and what doesn't make sense to add together or multiply? Well, adding points together, subtracting points from each other is like adding locations together or subtracting locations from each other. It doesn't make a ton of sense. Practically speaking, it doesn't make sense. We don't add points together. Sometimes we subtract them to get the vector between them. However, there are many types of modeling in applied fields, like outside of math. Economics is the one that stands out most to me, where a point represents an allocation of goods. So maybe you have apples and oranges or something like that, and person A has this allocation and person B has this many apples and oranges. You want to know how many total they have if they combined forces. Then you might be adding points together. But there's no sort of geometric significance for this in mathematics. Adding vectors together or vectors to points makes perfect sense. If you add two vectors together, you get another vector, just as we saw right here. If you add a vector to a point, you get another point, as we saw up there. But it's worth noting that in R2 and R3, especially when you're doing points and vectors, R2 and R3 are both excellent representations of 2- and 3-dimensional space. So they're used a ton in applied fields like geometry and physics. And geometry is obviously the one that we will be exploiting the most here. So let's take a look at our sample problem. We have 2 points in the plane, P and Q, and we also have 2 vectors that we're going to toy around with. And the question is really, for each of these, which of these things makes sense? Our first question is, what is Q minus P? Well, we kind of already did a little bit of a problem like that. Well, Q minus P would give us the vector that would take us from P to Q. We just want to subtract component by component. Note that I am being very, very clear that I have 2 points here and that the answer itself is actually going to be a vector. So this tells us exactly the increment of change needed to add to P to get to Q. We have 2.4 minus 1.4 is 1, and negative 4.8 minus negative 3.8 is negative 1. Moving right along. The next question is, what is P plus the vector V? Well, if we take a point, we add a vector onto it, we get another point. We do this component by component. So we have 1.4 minus 0.2 and negative 3.8 plus 1.3. Now, let's take a look at what happens when we subtract vectors from each other. We have V minus 1.5 times W. Now, computationally, this isn't too bad at all. Let's write it down. Remember that this 1.5 will distribute to either of these components in the second vector, and then we just want to take negative 0.2 minus 1.5 times 0.6. 1.3 minus 1.5 times negative 0.2. And that's our final answer, the vector negative 1.1, 1.6. Now, of course, doing this graphically, if we had V and W, these are not drawn to scale, but we're just going to see what happens graphically. And we want to take V and subtract off 1.5 times W. Well, the first thing is that I want to manipulate W. I want to multiply it by 1.5, so it is going to grow in length. Right, that's 1.5 W. And then negative 1.5 W looks just like that, but just pointing in the opposite direction. So really 1.5 W looks, negative 1.5, pardon me, W looks like this. And then if I wanted to add V and negative 1.5 W, I would want to line them up so that they are, here's V. Remember that vectors are not anchored at any particular place. They're increments of change, so you can move them around very nicely. So we have V here, and then 1.5 W looks something like that, negative 1.5 W. And so our total starts at the beginning of V and ends at the end of negative 1.5 W, and that would be our answer. And sure enough, you can see that this has a negative X component and a positive Y component, and that would mean that it's pointing to the left and upward, and so is our answer here. Our next question asks, what if anything is P plus Q? And P plus Q honestly doesn't mean anything, right? Summing points doesn't make sense in mathematics, so this is nonsense. But it is always worth pointing out that in economics, if these are allocation bundles, maybe it's friend A and friend B's apples and oranges, and they're teaming up to start an apples and oranges business or something, and so we add them together. In that particular case, depending on the actual significance in the application of these points, then maybe it makes a little bit of sense, but in general, no, this does not make sense. Last but not least, we have 0.5p plus 0.5q. It seems like that would be an illegal operation, but why is it okay? What would 0.5p plus 0.5q equal? Let's write it down first. So you see that our first step is really to distribute that scalar multiple out in front into each of the points. Then when we add them together component by component, what do we get? At first it seems like nonsense to add 2 points together, but what we're doing is adding half of each point together. What in fact we get using this recipe is the midpoint formula. So in this particular instance, it makes sense in computing the midpoint to add points together, but really in nothing else. Here's a great example of an economic application and how to reinterpret points and vectors in a different way. Let's take a look at this point. This interesting point here, P, could represent the economic situation in Nebraska, where labor costs $18.80 an hour, and the second component is transportation costs. That's $1.12 per mile, and wheat costs $34.70 per bushel. And so each of these components match to a particular cost of some good. And so here's Q might be the corresponding economic situation in Mongolia. Here's labor costs, transportation costs, and wheat costs. Now let's take a look at what happens when we want to implement some sort of increment of change. Even though all of these coordinates have different units, that's okay. A linear function like this would mean if we took this linear function where it takes 2 times the first component and 10 times the second component and 5 times the third component, note that x1 and x2 and x3 are the different components of within the point P, that would be a meaningful way to describe the total cost of a quantity of flour that required 2 hours of labor and 10 miles of transportation and 5 bushels of wheat. Well, let's take a look at this vector. What would that mean? The vector might be something like a new tax structure that makes labor costs 76 cents more per hour and transportation costs 12 cents more per mile, and wheat costs $1.23 less per bushel. So what's the economic interpretation of P plus this vector V? First, let's compute it. Now remember that a point plus a vector is another point. We have P, which is the economic conditions of Nebraska, and we have V, which represents increments of change from a new tax structure. What happens? What is the significance of the sum of these two things? What is the significance of this new point, P plus V? Well, it's the economic conditions in Nebraska after the new tax structure is put in place. Let's move right along. This is just a quick final closing note before we go into our group work. The standard basis is very important, and much of our work will be in the two-dimensional plane where all vectors can be made of the sum of multiples of 2 standard basis vectors. We call them E1 and E2. E1 is 1, 0, which is 1 increment movement in the positive x direction and nothing else, and E2 is 0, 1, which is a movement of 1 unit in a positive y direction and nothing else. So both of these have length 1 as far as their arrows go. And take a look that if you take an arbitrary vector in R2, like 3, 4, you can construct this vector using scalar multiples of the standard basis. 3 times E1 plus 4 times E2 will give you 3, 4. Now this seems really, really obvious, but it's actually really powerful. The vector 3, 4, when you look at it as an experienced mathematician, you say, oh, that's 3 in the x direction and 4 in the y direction. But really, when somebody who's not mathematically trained looks at this vector, it means nothing to them. It's just an array of numbers. And what gives it significance is that we, as mathematicians, are conditioned to interpret everything in terms of the standard basis. We take a look at that first component and we say that's movement in the x direction. We take a look at the second component, we say that's movement in the y direction. That's because convention dictates that unless otherwise specified, we will be working in the standard basis. Now, what I want to be very, very clear about is that what you really should be considering these as, instead of 3 to the right and 4 up, is that 3 and 4 are the coefficients on the standard basis vectors that when you take those scalar multiples of the same standard basis vectors and you sum them together, that's how you get your desired vector, 3, 4. So even though your intuition is to immediately interpret a vector in the standard basis, appreciate for a moment that a vector is really a set of coefficients. And unless otherwise specified, they're coefficients of the standard basis vectors. But later on next week, we will be in an instant where it's going to be more useful to use a different basis than the standard basis. And we'll talk about how do we translate from the standard basis to a different basis, but that's for another day. Understanding that the components of a vector are actually coefficients is really necessary to being able to comfortably work in other bases, instead of just saying, oh, that first component is movement in the x direction, the second component is movement in the y direction. Think of it as that first component is the coefficient on E1, which, yes, happens to be movement in the x direction. The second component is the coefficient of E2, which is movement in the y direction. And that's it for today. Take a look at the group problems. Also check out Seesaw, which is going to be in the link below as our class works on some of these group problems, where all the solutions to the group problems will go. And then the corresponding homework assignment, which will sort of take a few applications of all these different topics that we just talked about and give you a chance to get your feet wet with them. As always, don't hesitate to email if you have any questions, if you're still remote, finishing up your school year, or even if you're one of the day students, or come in with a particular question or head to office hours.